Hello, I'm Jacob Mennick, and I'm here to tell you about our work on multimodal few-shot learning with frozen language models. This is joint work with the team below, Maria Simpukeli, myself, Serkan Kabi, Ali Islami, Oriol Vinyals, and Felix Hill. That's me, and you can follow me on Twitter to hear my hot takes and a bunch of really dumb machine learning puns. The starting point for this work is what I think is kind of one of the most important discoveries of the last few years, which is that text language models are great few-shot text task learners. And this is, of course, exemplified by the GPT-3 team, which showed that a really big language model trained on lots of text can be really flexibly applied to lots of tasks just with kind of this few-shot prompting. What we've discovered in our work is that these big language models are also decent at image-to-text tasks, and they also show few-shot learning behavior in this setting, even though the language model was not shown any images during pre-training. All we have to do is show the model images encoded in a way that they understand. And what this work hints at is extending the interface of these impressively general language models to include not just text prompts, but also images. In this example from our paper, we show in a prompt a sequence of interleaved images and text, which shows this task of deciphering an image as a corresponding emoji, and it can generalize to a held out image to guess the right emoji that would correspond to it. Another really cool thing is that these text language models have learned lots of facts. And what we've kind of shown here is that you can access these facts with visual inputs, not just text inputs. For instance, recalling the name of an inventor, which was learned during pre-training, based on an image of an object. And fundamentally, this is about adjusting the interface of a text-in, text-out language model to include images in the input. So what happened was some of our colleagues at DeepMind trained a really nice 7 billion parameter language model on the open source C4 dataset. This is quite a standard autoregressive language model trained to predict the next subword token with the maximum likelihood objective. And it's a standard GPT-2-like self-attention model. The colleagues that trained this was Jack Ray, Trevor Kai, and Sebastian Bourgeot. And I want to thank them for producing these models so that we could study them. And when people approach few-shot learning with language models, they treat them as a machine with a text-in, text-out interface. In the input comes a prompt, and the output comes predictions for what might come next. In the middle, the text tokens are transformed by independent embeddings so that the model receives them as a sequence of continuous vectors. In our work, we focus on the vector input, text output part of the language model, which is just the self-attention stack. So even though this model was trained on text, as far as the self-attention stack is concerned, it's only seen a sequence of vectors. So to show this model images, all we have to do is present an image as if it was a sequence of embeddings of text tokens. To get these image embeddings into a form the model understands, we train the model to caption the image. That is, to produce the correct caption from the captioning dataset, given a prefix of tokens emitted by a convnet. We keep the language model frozen, both the embedding layer and the self-attention stack, and all the training that happens is the convnet learns to get the language model to produce the right caption. Crucially, we backprop through the frozen language model to get the gradients used to train the vision encoder, but the only thing that's trained is the convnet. So we kept the language model frozen because we wanted to study what it can already do without any further training, kind of for scientific reasons. We don't claim that's the best thing to do, but it turns out that we have some evidence that it actually generalizes better than fine-tuning. And the reason for this is that there's a huge asymmetry in the size of captioning datasets versus language modeling datasets. You could call it a dataset if you want, but it's really just a dump of text on the internet, right? Whereas captioning datasets require human labor to annotate. So they're tiny in comparison to the amount of text you can get to train a language model. And we do much fewer gradient steps in the ConvNet than were done to train this big 7 billion parameter language model. All our training was done on this conceptual captions dataset, which has an interesting property that it has named entities removed. And I'll say more about that later. But the interesting thing to keep in mind is that this means that we don't teach the model about named entities via the captioning task. So for instance, the ConvNet won't know anything about named entities. More on that later. By adapting the interface of a language model in this way, we kind of hope to unlock a new suite of tasks for this highly general few-shot learning behavior. For instance, tasks that require an image and text input and a text output. So one thing that we can slot into this framework is visual question answering, where we show a model of an image and we can ask stuff like what's the object in the image, what color is the object, and so on. We can also show the model interleaved images and text in the prompt in any order. It turns out that our system actually generalizes, even though that during training it was only presented with one image, it can generalize to seeing multiple images and image and text interleaved. And so this is what enables showing some examples of image-text correspondence in context. We can also try to phrase classification as this generative in this generative framework. So just sampling the string, this is a DAX, instead of emitting some kind of using some sort of softmax layer. And this particular task is one which we've developed, which I'll tell you more about. It's this fast binding task where we want to do classification of a held out image of a lion, say, but we don't let the model use the word lion. We teach it in context to bind this lion object to the word blicket, and then this husky to the word dax, and we expect the model to recognize new blickets, for instance. This is actually this isn't our new task. This is the way we attempt mini ImageNet. Our new benchmark is so-called fast VQA, where not only do we want to recognize new instances of these concepts that we of these objects, but we want to ask questions about these objects with the kind of bound nonsense names like dax and blicket. This is a new benchmark that we'll be releasing soon, and it's actually very tough. But our quantitative results show that the model is making use of this multimodal context in a very convincing way. The first baseline to look at would be a blind model, where it's actually not even allowed to use the images, they're just blacked out. One interesting finding is that these blind models are essentially just language models, right? So we already know they enjoy few-shot learning, which is why, for instance, in the VQA figure at the top, even the blind model's performance increases with more examples shown in context. But of course, showing them the image performs convincingly better, which kind of establishes meaningfully that it's making use of this context. Furthermore, these models improve their performance as you show them more examples. The other baseline for visual question answering is a fine-tuned model, which actually gets to train with SGD on some VQA examples. And it's pretty cool that we closed the gap substantially from zero-shot performance towards the SGD fine-tuned performance with just 4 examples. We consistently beat this blind baseline in the other tasks we attempt. For instance, the way we look at mini ImageNet and the way we look at fast VQA. Fast VQA is especially challenging, but it completely rules out any kind of blind behavior by design. Of course, these numbers I just showed you are nowhere near competitive with the state of the art, but that's not really the point. The point is that these models are exemplifying few-shot learning behavior, which is really exciting. So from an engineering perspective, there will be future work that will do this much better. And what we're kind of showing is that we can achieve this, we can attempt these tasks, we can expand the interface of the language model and show clearly that it's making it to the context. In the slides that follow, I'm going to do a deep dive into a qualitative example. And I just wanted to highlight that our model is not perfectly robust. There's a long way to go. So that there were multiple samples required to get past the kind of well-known language model failure modes, because we are sampling after all. But the behavior is extremely cool, so bear with me. So my favorite example from the paper is that we can show the model an image of an airplane and ask who invented it. And that model will look up in its knowledge that it was invented, the airplane was invented by the Wright brothers, and tell us. What I've not shown is the prompt that was able to enable this behavior, and I'll get there. But first, I want to remind you that conceptual captions doesn't have any named entities in the text. They've all been removed and replaced with words like person. It's called a hypernyming. So I said before that conceptual captions, the data set, does not have named entities. So when we just get our model to caption, we don't show it any text, just an image, which matches the training setting. It emits a conceptual captions-like caption. So it says, this is an airplane flying over the blue sky. And then you see some kind of noise where it's a stock photo and there's some random symbol. But when we don't show it, when we don't give it any text prompt for what we want the output to be, it defaults to captioning and matching the behavior of the conceptual captions data set, right? And when we treat this as an object recognition task by asking, what is this in the prompt? It tells us that this is, okay, a supersonic aircraft over the skyline. Not a great answer because there's no skyline here and we don't have any reason to believe it's supersonic, but it is attempting to kind of do object recognition. Cool. We know this this model knows that it's an airplane. That's good to verify. And then when we ask it point blank who invented the thing in this image, it tells us in these really vague terms, again, matching the conceptual captions data set format. But what we can do is we can prompt the model to show it what we really want to know, which is the name of a person who invented this thing, right? So when we show it in context, a few examples of this, like a microscope, which was invented by Zacharias Janssen, and a Model T, which was invented by Henry Ford, this reminds the language model that it knows about named entities. I learned about loads of named entities during language modeling pre-training, right? And what this prompting is able to do is remind the model that it knows about named entities and encourage it to please give us a named entity as the output. And after this kind of prompting, it can do this external knowledge visual question answering, which is really cool. And I think it's a pretty convincing example of a kind of multi-hop reasoning where the convnet does object recognition, and then the language model can do kind of information retrieval and factual recall to tell us that this thing we pointed the camera at was invented by the Wright brothers. So that's it. Thanks for your attention, and thanks again to my lovely colleagues who made this project a joy to work on.